Hello, for today's video we're talking about alternating series. So we're going to talk about the alternating series test and also classifying convergent series absolutely or conditionally. We are skipping using the remainder theorem for an alternating series and using that to approximate the sum of the series, as well as what happens when we rearrange the terms. So if you're interested in those topics, you can look those up in your textbook. So what is an alternating series? An alternating series is a series of the form -1 to the n times a sub n, or -1 to the n plus 1 times a sub n. And so the piece in the front, the -1 to a power, makes it so that my terms go from positive, negative, positive, negative, positive, negative. And we want to clarify that this other piece is always positive. Okay, so these types of series converge when two conditions are met. The first one is that positive piece, the a sub n, goes to 0 as n goes to infinity, and it's decreasing. So a sub n plus 1 is less than a sub n for all n. So let's use this alternating series test on a few examples here. So the first example is determine the convergence or divergence of the series from 1 to infinity of -1 to the n plus 1 times 1 over n. So my first thing I'm going to do is I'm going to look at the limit as n goes to infinity of the non-alternating part. So that is just 1 over n. And that in fact does go to 0. So my first condition is met. The second condition is that a sub n plus 1 is less than or equal to a sub n for all n. So that would be 1 over n plus 1 less than or equal to 1 over n, which is in fact true for all n. So then I would say that yes, this converges by the alternating series test. Okay, my next example here, I have the series from 1 to infinity of n over -2 to the power of n minus 1. So I'm going to rewrite that. And I'm going to pull out a -1 to the n plus 1. And so basically n plus 1 and n minus 1 are both odd at the same time and even at the same time. So I'm just doing an n plus 1 so that it matches my theorem more precisely. But if you did n minus 1, that is completely fine too. And then n over 2 to the n minus 1 would be my a sub n piece. Okay, so my first condition is the limit as n goes to infinity of n over 2 to the n minus 1. That's going to be infinity over infinity, so I got to use my good old friend L'Hopital. So then I get the limit as n goes to infinity of 1 over, natural log of 2 times 2 to the n minus 1. So then that in fact does equal 0, so my first condition is met. My second condition, I need to show that n plus 1 over 2 to the n is less than or equal to n over 2 to the n minus 1 for all n. That's not as obvious as it was in the previous example. So what I want to do is I want to make that my last step. And I'm going to work backwards a little bit to show that I started with something simple. So my last step here is going to be that n plus 1 over 2 to the n less than or equal to n over 2 to the n minus 1. So that shows a sub n plus 1 is less than or equal to a sub n. So to make this a little simpler, I'm going to go ahead and put the factors that look like each other next to each other. So I'm going to multiply both sides here by, let's see here. If I multiply both sides by 2 to the n minus 1, and 1 over n. So then I'm going to get, n plus 1 I mean. So then I'm going to get 2 to the n plus 1, minus 1, over 2 to the n is less than or equal to n over n plus 1. And then I see that here I can cancel on the left-hand side, I can cancel 2 to the n minus 1, and I'm left with 1/2 less than or equal to n over n plus 1. And we see that is in fact true for all n greater than or equal to 1. Okay, so basically what the idea here is I start with something simple that is an obvious statement, and I build it up from there, okay, to get to what I'm trying to show, okay? So working backwards on these is fine. If you want to like go through and start with your inequality, do the steps, and then rewrite them in the opposite order, that's great too, okay? So then we can say, yes, both conditions are met. So thus, my series from n equals 1 to infinity of n over negative 2 to the n minus 1 converges by the alternate series test. Great. Next example. All right, so these are two examples when the alternating series test does not apply. So in this first example here, we see that it does not apply because the limit as n goes to infinity of n plus 1 over n equals 1, which is not equal to 0. So that does not meet the first condition. And in the second condition, if I just look at my terms without the positive or negative, I have 2, 1, 1, a half. Okay, so it's not always decreasing. 2/3. Okay, so this right here is an example of the second condition not working. So a sub n plus 1 is not less than or equal to a sub n for all n. Okay? All right, next example, absolute and conditional convergence. So a theorem says if the series of the absolute value of the terms converges, then the series also converges. So one example of this where the converse doesn't work, so this is a warning. The converse is not true. Okay, so an example of that would be, we see that the series n equals 1 to infinity of negative 1 to the n over 1 to the n converges. Okay, that was our first example. But the absolute value of that, which we know is the harmonic series, does not. Okay, so the converse is not true. All right, next. Definitions of absolutely and conditionally convergent. So a series is absolutely convergent when the absolute values of the terms converge, and the series is conditionally convergent when the series converges but the absolute values of it diverge. Okay, so here we go. Let's look at some examples. So determine whether each series is convergent or divergent, and then classify any convergent series as absolutely or conditionally convergent. Great. Let me get some space here. So our first example is negative 1 to the n times n factorial over 2 to the n from 0 to infinity. So let's look at this. So we have 0 factorial over 2 to the 0, and then minus 1 factorial over 2 to the 1, plus 2 factorial over 2 squared, so on and so forth. So if I just look at the limit as n goes to infinity of the a sub n, so ignoring the alternating piece, I have n factorial over 2 to the n, which does not equal 0. Okay, so the series diverges by the nth term test for divergence. And you can put the negative 1 on there if you want to. Okay, so we don't have to classify this one because we only classified the convergent series. All right, so my next one, let's look at this. So now we have an alternating series, 1 over the square root of n. So let's look and see, using the alternating series test, what happens here. So if I take the limit, 1 over the square root of n, that does in fact equal 0. And then my second thing is the square root of 1 over n plus 1 is in fact less than the square root of n. So we know that this series converges. by the alternating series test. Okay, but if I look at it without the alternating piece, that is a p-series with p equal to 1/2, so it diverges by the p-series test. So then we would say that this series here is converges conditionally. All right, let's look at some more examples. Determine whether each series is convergent or divergent. Classify any convergent series as absolutely or conditionally convergent. All right, so what I'd like you to do is, since you are in person today, go ahead and pause the video now. Try these with somebody next to you if there's somebody ready to work, or I'll put you in breakout rooms if you want, if some of you are at home. And check them out, decide what you think, and then press play on the video and see what the answer is. Okay. For this first one, -1 to the n times n plus 1 over 2 to the 3n. Okay, so let's figure out how this one works. So I have -1/3, -1/9, +27th, +181st. So this is not an alternating series, okay? So it's not an alternating series, which is kind of a bummer, so I can't use the alternating series test. So let's take a look at the absolute value of the terms though. So if I have this -1 to the n over, times n plus 1 over 2 to the 3n, okay? So this is just the same thing as n equals 1 to infinity of 1 over 3 to the n, which is a geometric series, okay? So this is a convergent geometric series, since 1/3 is less than 1. So then we can say that my original series, n equals 1 to infinity of -1 to the mumbo jumbo over 3 to the n, is absolutely convergent. Great. Let's look at B. So for example, B, if I took the limit as n goes to infinity, this is an alternating series. Great, so that's fantastic. Let's take the limit as n goes to infinity of 1 over the natural log of n plus 1. And that does in fact equal 0. And if we also look at 1 over the natural log of n plus 2, which is my a sub n plus 1 term, that is less than or equal to the natural log of n plus 1 for all n. Okay, so I know my series converges. By the alternating series test. Okay, but if I think about taking the absolute value of it, this is going to diverge by, I'm going to use the direct comparison test. And I know it's going to diverge by the direct comparison test because 1 over n is less than or equal to 1 over the natural log of n, or natural log of n plus 1. And since the smaller series diverges, it implies the larger series also diverges. So in this case, I would say that my original series from n equals 1 to infinity of -1 to the n over natural log of n plus 1 conditionally converges. All right, That is all I have for you today, so go ahead and try